Okay, hello everyone. This is the final exam study session for CIT 247. Now, depending on what section you're in, I believe Dr. Assad said for the in-person section, you'll all be covering modules 10 to 12. For the online section, I think he's also putting subnetting in your exam. That may be an error. I don't know for sure. He hasn't said anything, but if you all in the online section need to study subnetting, I highly recommend you go back to my previous study session. Um, I'm going to try to keep this kind of quick because the in-person section has to literally take this test today, and YouTube's going to take a while to upload everything. So we're going to go ahead and get started. Now, there also is not a study guide PowerPoint this time. That's because I don't know what's on the quiz or the test. And last time I did that, I feel it was rather inadequate. I talked to a student. He said that a lot of things that were in that test were not in my PowerPoint. I am very sorry for that. I don't know what's on the test. Dr. Assad is making these tests as they come. So unfortunately, my schedule does not permit for me to wait for him to make these tests and then make them because he kind of releases them on the same day they're available, or he's giving them out. So in the interest of just to make sure you all are covered, I'm going to cover these last three modules in this class. Just as long they're pretty short PowerPoints overall. Just read the last three PowerPoints a few times over. If you do that, you should be fine. But we're going to go ahead and get started with STP and Ether channels. So I would say keep an eye out for things in your PowerPoint that could become a question. I don't know how Dr. Assad makes exam questions, but if you've gotten used to how he does it, you might see patterns in how he uses stuff in the PowerPoints. But just pay close attention to details in the PowerPoints. You should be fine. But anyway, let's discuss redundancy in networks. So redundancy is a crucial feature that helps maintain network availability. Redundancy is a good thing. So if you see in this diagram here, we got these four switches here. Notice how there are multiple paths this PC can take to get to PC2. So PC3 can go like IUU3 to IUU4 to IUU1, then to 2, and then to PC2. It could just take the straight path. It could go like IUU3 to IUU4 to IUU2. Now that's great, and that's really a way a network should be because if, for example, like you've seen this symbol here, if a cable just died, let's say for example, or a switch port was broken, with redundancy, a PC has multiple paths to take to another PC. There's still other paths available. So placing multiple links between switches is good because it can keep data flowing even when the link goes down, as you can see with this symbol here. When these links go down, there's still other ones that are available. Redundancy is great, but it causes issues with switches. So while having redundant links between switches is helpful for availability, these links, when configured alone, can cause multiple problems. One of these is broadcast storms. This is when broadcast frames are being repeatedly forwarded throughout a network, causing needless bandwidth consumption. This can be caused by just one frame looping between switches. Broadcast storms are the root cause of the other two listed problems here. So there's also MAC table instability, continual updating of a switch's MAC address table with incorrect entries. This is the continual updating of a switch's MAC address table with incorrect entries in reaction to looping frames, resulting in frames being sent to the wrong location. And finally, there's multiple frame transmission, which is where looping frames can create multiple copies of the same frames being received by destination devices, which can confuse some applications. So having multiple cables and switches is very confusing because broadcast frames can really confuse things. It can cause a lot of problems. So that is why we use STP. That is the reason we use STP. It is to prevent broadcast storms and therefore prevent these other two problems. So the STP ensures that your network has good bandwidth or good performance, and also ensures that devices don't deal with all this crazy stuff here. By the way, you might want to be able to differentiate between these three types of problems. That to me sounds like a problem that could be in your exam. That's just guessing. I don't know for sure. So if you're wanting to know how broadcast storms work, um, Here's a little diagram that came from the other professor I put in here. So the following demonstrates how a broadcast storm forms in a LAN with redundant connections. So let's say old Bob is here, and he sends a broadcast from his MAC address here. So the switch 3 here forwards this broadcast to both the switches. This is a broadcast frame. It's going to go everywhere. So the third switch here learns that Bob is on this port. So the second switch forwards its broadcast to to the other switch here, and then switch 1 does it again to 3. And then switch 3 learns that Bob is on port, or switch 3 learns that Bob is on this port here. So it may be confusing, but it just causes everything to be messed up. So it confuses switches, basically. It sends broadcast frames and ARP communications all over the place, and it really confuses switches to where devices are located. I hope that made some sense. But anyway, just know that broadcast storms are really confused switches. They cause broadcasts and ARP messages to be sent over and over and over and over again, and they end up being recorded wrong. MAC addresses end up being recorded wrong in these switches, which can bring traffic to a halt in a network. Also, the amount of data that these switches are handling can also cause switches to crash. Little fun fact. So this is where STP comes in. Spanning tree protocol prevents looping frames by setting certain switch ports to forward frames and those to block them. If you see this diagram here with this BL, the square here, these are blocked. So you can see there's no redundant connections between there's no redundant paths between PCs. Block ports do not process incoming frames, learn MAC addresses, and do not forward any frames except for STP and RSTP messages. So in other words, they tell other switches that, hey, these ports are blocked. That's about all they do. They aren't going to accept traffic. Port statuses are automatically updated when ports or devices are down. The one downside to STP, however, is a considerable decrease in performance. So yeah, STP may cause like the direct path to between two PCs to be shut down. So if you see like PC3 and PC1 here, because of STP, we do have to sacrifice some performance by blocking this direct port, or blocking this port that directly connects PC3 to PC1. I mean, it is a loss to a degree in performance, but I mean, it's better than having your whole network crash. So port statuses are automatically updated when ports or devices are down. So in other words, if a cable goes down, this whole STP process will refresh and different ports will be blocked. So RSTP is an improved version of STP that uses an improved algorithm to significantly reduce convergence time. Less than 10 seconds for RSTP, and it's up to 50 seconds for STP. So more on RSTP's differences from STP, including its algorithm, can be found in your textbook starting from page 228. That should be the volume 1 textbook if I recall correctly. Let me see what was it say. I don't remember. But anyway, yeah. RSTP is what you configured in your lab, or are configuring, depending on your progress in that. But I don't think you'll be testing this part. You might want to read up on it just in case. You might see something on it. I don't think you will, but just in case, read this. Briefly glance over that just to be safe. So STP configuration, root switch selection. Before I continue, I'm going to pause a minute. Just send through chat or just say yes or no. If any of you have any questions so far. Okie dokie. Sounds good. Thank you. So root switch selection. The process by which our STP or RSTP selects switch ports to disable is automatic, but can be influenced through manual configurations. So when the RSTP process begins, it starts. It begins by selecting what is known as the root switch. For brevity, I'm going to just say RSTP from here on out. They're kind of the same thing, but we're going to just say RSTP because that's what you configure in the lab. So references to STP will also be relevant as RSTP. Yeah, that's just like I was saying. We're just going to use RSTP, and it's going to mean both throughout the rest of this presentation here. So the process starts by electing what is known as the root switch. This is the switch with the lowest BID, or bridge ID. Let me zoom in on that a little bit. A minute here. Okay. Can you see these numbers fine? I'm just zooming in for those who are viewing the video. But so if you see these numbers here, the way you calculate the bridge ID begins, as you could read here, begins with, um, or do we, let's see here. Oh, okay, we do explain here. So the priority value is first checked. So the lowest bridge ID is a combination between the switch's priority value and MAC address. The priority value is these first three or first five numbers here, the very first thing in the bridge ID. So the priority value is checked first, which comprises the first five numbers of the bridge ID. If they are the same between the switches, the MAC address is then compared. So in this root switch election here, we could see that these two here, these numbers, the 409 or 40,960 compared to 32,768, these two numbers are lower. Therefore, these are candidates for the root switch. These two are not. Now, there's a tie between switch 1 and switch 2 here. They have the same priority value. Therefore, the MAC address is checked. So the lowest MAC address is the one that's going to become the root switch. So first you find the lowest priority value in the BID, then you find the lowest MAC address. In this case, it's IOU1 because all the very first numbers here are ones. These are twos. The MAC address in IOU2 starts with twos. Therefore, IOU1 is the root switch because it has the lowest bridge ID and lowest MAC address. I'm going to go ahead and zoom out. Let's see. Okay, there we go. Yeah, let's zoom in one. Okay, sorry about that. Okay. STP configuration port states. After this election occurs, all the ports in the LAN are placed into one of the following states. So in other words, these are all the switch ports, by the way. So there are root ports. These are ports on the switch that lead to the fastest path to the root switch. Each switch only has one. Then there's designated ports, which are determined per link between two switches. The switch with the lowest cost to route between them gets the designated port. And then finally, the blocked port. Ports that are disabled on the switches. Selected alongside designated ports, the switch having the greater cost to route receives the blocked port. So port costs are determined by manual settings and the default speed a port can handle. The following table, which contains default port costs, might be helpful in future quiz or exam. This was when I designed the exam and the quiz. There was actually a question where you actually had to map, or you actually had to go through this whole process and answer which one was the root switch, which one the block ports, root ports, and so forth. That was actually a test I designed. I don't know if Dr. Saad's going to make one like that. I don't know if he's going to make a problem like that. To be safe, just review this table. Make sure you know the default port costs based on internet speed and port name, whatever. But yes. Yes, that's true. Professor Cunningham actually made that. We used Cunningham's exams and stuff when that was. Yeah, that was a tough exam, I think. Yeah, that was. I had trouble. I even had trouble with that question when I was a student. Tough question. That's why I wrote all this stuff because we didn't have stuff explained like this when I was a student. That's why I made this PowerPoint. Hopefully, explain it a little better. Hey, John, just out of curiosity, does this help you understand a little better so far? Do you think that what I've written here explains this process a little better? Good. Excellent. Thank you. So once the bridge ID or excuse me, the root switch is selected, we are then, based on this information here, the port costs, we then determine the root ports. So we're actually going to go through a full-on STP example again. We're going to figure out another root switch and all that other stuff. Actually, I think it's the same diagram, but anyway, so the whole STP process or RSTP process is going to be explained through these next few slides. So the first step is determine the root switch. Compare the switch's BIDs, start with the lowest switch priorities, the first five numbers, and in case of a tie, check the MAC addresses. Switch to the lowest priority and then the lowest MAC address becomes the root switch. Here, IOU1 becomes root. It's the same numbers from last time. These two have IOU1, IOU2, if you see here, have a lower bridge or priority value than IOU3 and 4. Therefore, these two switches down here are not counted, but these two are in election now. And IOU1 has the lowest MAC address, so therefore it would become root. So next is to determine the root ports. This is where you find the ports on the non-root switches that provide the fastest path to the root switch. This is typically the port that is directly connected to the root switch, but not always. You got to be paying close attention to those port costs. So for example, IOU2, GH or G0/0 are these ports all become root. So I labeled them with the green thing here. I'm going to explain something here. So if you see these ports here between IOU1 and IOU2, these are gigabit ports. This is just for the sake of conversation. I added this here. Your switches in GNS don't actually have this. I actually used PowerPoint and made these images, but yeah, so these ports here are faster than these Ethernet ports, just to let you know. It's going to be important later. But right now, so when you're determining what is going to be the root port, you need to look at a switch that's not root. So this one's root, IU2 is not. And you need to check which path it has to reach IU1. Now, this port cost here would be the lowest. Now, excuse me, let me start that over. So when you're comparing the different routes, you can go like IU1 to IU2 to IU1, the direct path, IU2 to IU3, and then IU1, and then you could do IU2 to IU4 to IU1. So this port here, right, this path here is the fastest one. There aren't any specified port costs. So if we add like a port cost of 1 on IU4's E2/0, and then added a 1 or port cost of 1 on E1/2 of IU1, that would make this port the root because this would be much faster. But all the port costs are default, and I believe Gigabit has a default port cost of 19. Oh no, it's 4. And then the Ethernet has a default port cost of 19. So this is a port cost of 4. This would be 19 plus 19 going to IOU3 and then IOU1. And then it'd also be 19 going from IOU4 to IOU1. These are all default port costs. So by default, the path to IOU1, direct path to IOU1 is the fastest, and therefore that port on IOU2 becomes root. And it's the same for the other two switches. The direct path is the fastest one because the port costs are default. Because when you go around, you have to add the port costs together. So that's for IOU4's case, that would be 19 to go to IOU3 plus 19 to go to IOU1. That would be 38. But IOU4 can just go straight to IOU1, and that would be just 19 because these are Ethernet ports. So 19 is less than 38. Therefore, this port is the fastest one. Now, even going this way, you would have 19 plus 4, and that's 23. That's still greater than 19. Let me ask you all. This has been a little difficult to explain. I just wanted to make sure. Do you all understand what I'm saying? You can just put in the chat. Do you understand what I'm saying so far?
Yes. To me, everything here makes sense, but I do have a really quick question.
Yeah.
And this is kind of going back to, I think, the last slide or two. But how is a priority value generated? Not the bridge ID, but specifically the priority value.
Very good question. You can actually set those up. There's actually the default number. If you remember the textbook, I believe it says there's a default number that it's given. I don't know what it is. You shouldn't be testing on it, but there is a default value when you set up RSTP. A default priority value is given. You can actually customize that though to be lower if you want a specific switch to be root. So
Okay.
it depends on how you configure your switches. And I believe in your lab you actually can just tell a switch to be root. It might end up getting a lower priority value. I'm not sure what that command does. I'm sure it does something like that, but there is a command you could run on your switch to just make it root. You did that in your STP lab, if I recall. So once these root ports are determined, then we have to determine the designated block ports. Does that answer your question, Ben? I was just wanted to make sure.
Yep, that was perfect. Thank you.
Welcome. Can you all see with this size, I'm just kind of curious. Can you all see with zoomed in this far? Good. Okay, just want to make sure. So once the root ports are determined, then the last part, or one of the last, yeah, the last part of STP is determining the designated and block ports. That happens simultaneously. So all ports on the root switch become designated. That's the easy part. When you have your root switch will just have all designated ports. It doesn't need root ports because it's the root switch is itself. It's not trying to get to itself. It doesn't care. We're just gonna it just gets designated ports. Now, how you determine the designated ports for the other switches, that comes down to a process of so you have to compare the connections between the switches. So you would do IOU2 versus IOU3, or for example, so these connections right here, E0/2 and E0/2 on IOU2 and IOU3, you basically take the link and you compare both ports on that link. So IOU2 versus IOU3, in other words. So so you compare the two switches connected by these ports. The switch with the lowest cost path to the root switch receives a designated port, and the other one receives a block port. So IOU2's G0/0 port has a lower port cost than the Ethernet ports. So you can see here, this root cost is 4 for IOU2 because the gigabit port. IOU3 has an Ethernet default port cost is 19. So IOU2 can get the root faster. Therefore, between IOU2 and IOU3, this link here, IOU2 gets the designated port, IOU3 port gets blocked. So for the comparison between IOU3 and IOU4, so IOU3 versus IOU4 here, the former switch's root port has a lower cost than the latter switch's port, so it gets a lower one. So yeah, I put this right here. So the default port cost is actually 30. I actually made this, so we're going to pretend it's all 30, but the gigabit port costs 4, and the E1/0 costs 29. So that's for IU3. IU3 has a port cost that's lower. I put that down there. Because there's a lower port cost compared to IU4, it was set manually. The IU3 gets the designated port, IU4 gets the block port. Now between IU2 and IU4, it's the same story. IU2 already has the gigabit port, IU4 does not. Therefore, IU2 gets a designated port, IU4 gets a block one. Just to make sure, does that process make sense? Do you understand what's going on here? Where we're comparing two different ports on a link between two non-root switches? Does that make sense?
Yes, I do have another question though.
Yes, go right ahead. Ask as many as you want.
Specifically looking at this diagram, I see that E2/0 on IOU2 is a designated port, but it's going to a blocked port. And that's the same with IOU3. It's a designated port on E3/0. Why are those designated ports not blocked ports if they can't communicate to IOU4?
Good question.
That makes sense.
Yeah. So traffic can get to everything else. It just has to go around a lot. So it's just the way STP works. It isn't always going to result in the most optimal connection. So a port will be designated. It'll lead to a block port. It's just it's just the way it works. I'm not really sure why, but it just works that way. It's really the best way I can put it. So if a PC and IOU4 need to communicate with anything else, it just needs to go up to IOU1, which IOU2 and 3 it can already get to. So there's no problem with anything communicating down here from IOU4 to anything else out here. If something from IOU2 wanted to communicate to IOU3, all it has to do is go to IOU1. So basically, if a computer wants to communicate outside to another behind another switch, basically, everything has to go to IOU1 basically. Does that make more sense?
Yep. Yeah, that makes sense. Thanks.
Welcome. So yeah, it is kind of weird how it works, but it's just the way it works. We just accept it. Just gotta accept the way this is the way it is. Yeah, if you recall in your lab, you had to reconfigure the port cost to make sure your ether channel would not be blocked because you were competing with a direct connection to the root switch from another port. So you had to make that port's cost or one of the other port costs higher to make sure ether channel wasn't blocked. I tried to use a diagram to make that explain better. You know, a fun fact is when I was a student, we did not have that lab document. I actually made that one semester. It's the very first, that's the very first lab content I've ever made, and it inspired me to redesign this class. These PowerPoints, much of the content is from Cunningham, but I also added my own. Like all these explanations came from me. I made these all, but because this process is difficult, it took me a while to write this. This was difficult to write. It's a difficult process to understand, admittedly. I would say pay close attention when you break it down into these steps and you understand what the steps are and what happens in them. It becomes a lot easier to understand this whole process. Just pay close attention to the port costs. Know the default port costs. Thank you, John. I'm really happy to know that. Yeah, this process needs to be explained. I don't think the textbook has a clear enough explanation personally. This was hard. Yes, it was. Thank the Lord I got it right. It was hard. But yes, I don't know if you're going to actually have to do this process with a diagram. I seriously doubt that, but you might have questions about how it works. You might end up having a written explanation of this. I don't know what Dr. Assad is planning. Just break it all down into these 3 steps. Just understand what happens in each step. Take your time to understand it, and this process should be pretty easy to understand. Make sure you pay attention, like I was saying, to the port costs that are default to specific ports, like gigabit versus Ethernet, and then also look for numbers that are talking about port costs, like custom port costs too. We just have a page on ether channels. There isn't much to say about them. Ether channels are simply logical links that are comprised of multiple physical cables. Basically, it's a way to combine multiple cables or logically combine multiple cables into one. So ether channels are configured by combining parallel links of equal speed between switch pairs into a single link. They are combined to significantly increase performance and redundancy. Ether channel links only fail when all connections fail. Yeah, that's all you need to know. Not much to see here. Better hurry. I know your time's running out, Ben. I'm going to try to go a little quicker. IPv6. Much of this is just fact memorization at this point. So it's good to know why we use IPv6. All non-private IPv4 addresses have been allocated. Solutions such as NAT and VLSM have helped, but there are still not enough IPv4 addresses to support the rapid increase of devices populating the internet. What do I mean by that? So think about it. A long time ago, we didn't have smartphones that got on the internet. Now we do, and they each have an IP address. But consider this. Not only do these phones have IP addresses, think about other things that get on the internet. They need an IP address. Your car, it's becoming to the point where your car, your washing machine, your refrigerator, your light bulb, your security system all needs an IP address now. It's all getting on the internet. Whether you like that or not, it's kind of the way things are going with this Internet of Things. And IPv4 cannot support that, and that's why IPv6 exists. It offers many benefits over IPv4. It supports 2 to the 128th power, 340 undecillion devices. My goodness, I don't think we'll ever drain that. I mean, it also has added security through built-in IPv6. Better support for mobile devices, supports multimedia quality of service features, has header improvements by removing the need to recalculate checksum, and negates the need for NAT address translation. Interestingly enough, I work in IT. Oh, let's see. The complicated second cousin that has multiple issues, but it's their life. Yeah, that's a good way to put it. One good thing about IPv6, thankfully we don't have to use it so when you work in a network, like for example, I work in NKU in the IT infrastructure team. I work with internal stuff sometimes with the switches. I don't need to work with IPv6. IPv6, you really don't need to use in a LAN. There really is no need because basically there are technologies to translate between IPv6 and IPv4. So all the IPv6 stuff can be outside the network, and then inside the network you can have private IPv4 addresses. That's the way I'm guessing that's the way a lot of organizations do it, including NKU. It's how we do it. It makes life a lot easier. There's really no reason to use IPv6 inside your network because it doesn't matter how. I mean, there is a limited number of IPv4 addresses that are private, but I mean, if it supports your organization, I mean, you can use those all you want. But anyway, that was just a little rabbit trail. IPv6 address design. IPv6 addresses are 128 bits or 32 hex digits, compared to 32-bit IPv4 addresses. IPv6 addresses are comprised of 8 colon separated quartets, with each one having 4 hex digits. So you can see here 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 is 32. That's why we say it's a 32 hex digit. So each of these numbers are hex numbers. Hex number or hex digits can have a value between 0 to 9 and then A to F. IPv6 addresses can be abbreviated with the following rules. Now this is important to pay attention here too. So you can remove leading zeros in a quartet. So for example, if you have 0002 in 0011, that can become just 211. It makes it a lot easier to read these things. Quartets with only zeros are sometimes replaced with 1 0. Consecutive quartets with only zeros can be abbreviated with 2 colons. Note that you can only abbreviate one set of quartets. So it's best to do, if you see in this example here, you can take there's like 3 quartets of zeros here. There's 2 quartets of zeros here. We should abbreviate the one with 3 to make the address as small as possible. And what you could do with these two, you could just put a 0. So if you see here, this abbreviation, so FE00, and then we have a 0 in the second quartet. All 4 of these zeros become 1 0. Same for the third quartet. Then we have 1. And then all 3 of these zeros disappear, and then we have 56. Note that you cannot remove zeros that come after a non-zero number. Those zeros have to stay there. So like your FE00, you have to keep those zeros. If they're leading zeros, you can get rid of them. If they're not leading, you keep them. And also, you can only abbreviate one set of consecutive zeros. Like here, that's not correct. You don't do that. Here's some basic differences between IPv4 and IPv6. 32-bit versus 128-bit. That's what an IPv4 address looks like. What an IPv6 address looks like. You don't need to abbreviate IPv4. You really can't. IPv6 you do. Local host address is 127.0.0.1 for IPv4. It's just ::1/128 for IPv6. Possible addresses it's like 4 billion. But IPv6 supports like 340 undecillion, ton. So IPv6 has different address types. So there's unicast, which is an IP address, Unicast are IP addresses assigned to a single interface for the purpose of allowing that one host to send and receive data. Unicast addresses are similar to those in IPv4. They start with 200. Multicast IP addresses that represent a dynamic group of hosts for the purpose of sending packets to all members of that group. So it's not broadcast, it's multicast. So then there's Anycast, a design choice by which servers can support the same function can use the same unicast address. Used when messages can be sent to any member of a group but does not need to be sent to all. It can be used for load balancing. So multicast is kind of like your broadcast address. It's pretty similar. Anycast, used for that. It's kind of like sharing an IP address is what I'm guessing. Unicast is kind of like your typical data flow. It's just one address communicating with another. So there are also other different types. There's specific types within unicast and multicast. So there's the global unicast. There's these facts here. I would say it's going to take me a long time to read for them. For the interest of time, just make sure you memorize some of the stuff here. I would say global unicast, it's important to remember that they're public addresses that allow communication over the internet without NAT. Unique local are private and used for the communication within inside an organization. They're not routable on the internet. Link local is only for communication within a subnet. And then link local multicasts are multicasts that stay in a local subnet. I would say do like pay attention to the addresses that belong to these. You could just do that by looking like at the first number. It's like FD is unique local, FF is link local multicast, and FE is link local. That should help you memorize that for the quiz. I don't know how hard Dr. Assad's gonna go on this, but I'd say pay kind of close attention to this. Then there's more IPv6 address types. There's reserved addresses. They begin with 00 and they're reserved. They're kind of like your class E addresses, I'm guessing, in IPv4. These unique local unicast. These are internal only and cannot be forwarded on the internet. Then there's loopback address. It's the one and only loop address in IPv6 is 7 zeros and 1. It's kind of like your 127.0.0.1, your local host address. Then you have your unspecified, which is all zeros. Used when a device does not know its own address. So there's a little bit more on link local addresses. Link local addresses are only used by devices in the same LAN. Routers would not forward link at local addresses. This was kind of to put here for your lab, but link local addresses have the following purposes. They're a source address for NDP, and they're for like an address for a next hop router. Basically, I think they are there to help your computer find the router in its subnet or default gateway. Link local addresses can be identified by FE80 ::/10. They begin with FE and ends with the EUI64 interface ID. We'll discuss that in a minute. So IPv6 routing. For a router to route IPv6 packets, it must have IPv6 routing enabled and have an IPv6 address configured in its interface. So it's kind of like a connected route. You go to conft, you can take IPv6 unicast routing, then you should shut down the interface and then add an address, basically. Well, actually, that may not be completely true. I think just enabling this should give like your router an IPv6 address, or you need to configure one. Can't quite remember. But there is a IPv6 address that's not configured, and then there's one that is. So it depends on the type, like you learned in your lab. The IPv6 addresses can be either be configured manually or by using EUI64. Oh, that's what I meant to say. Yes. So you can either manually configure an IPv6 address or use this strategy here, IE or process. The latter method requires you to use an IPv6 subnet alongside EUI64 on your router. So you can conft, you put on the interface, and then type IPv6 adder. You type your subnet ID, IPv subnet, and then type /64 and EUI64 at the end. This method then automatically creates a new IPv6 address with a router interface by using a specified process, which is detailed here. IPv6 addresses are divided into two parts, a prefix and an interface ID. These are respectively similar to IPv4 subnet IDs and host addresses. The EUI64 process then works with the router's MAC address to create the interface ID with the following process. So the prefix, I believe, is pre-configured, and then like up here, you configure this prefix, and then the interface ID is created with the following process. You first split the 12 hex digit MAC address into 6-digit halves. You insert FFFE in between the two halves, and then invert the 7th bit in the interface ID. The pages in the textbook here, 561, 562, better explain this. I don't know how detailed you really need to understand it, but just know how just know the steps. These 3 steps are going to be important to remember, I'm sure. So then there's NDP and Slack. So IPv6 uses Network Discovery Protocol as a replacement to ARP. NDP can be used by computers to use stateless address auto configuration to dynamically receive IPv6 addresses from a router. It basically replaces DHCP. It's pretty cool. However, IPv6 networks can still use DHCP for stateless address configuration. The following steps are used in NDP. The computer uses NDP and its link local address to send a router solicitation to its default gateway. The messages are sent as multicast packets. The router receives the RS message and responds by sending an RA message, a router advertisement. These messages are also multicast packets and include the router's IPv6 prefix. So note how you configure this IPv6 prefix, and then the computer receives this RA message and uses the EUI64 process to create a new address with this prefix. So any questions before I move on to the next PowerPoint? I know some of this is kind of complicated, but Just knowing the basic facts should be enough here. Thank you, Ben. I will, Ben. Be sure to look at the final PowerPoint later today, the ACO one. That's good, John. Anything you want me to maybe explain a little better, perhaps? Is there something you want me to go over again? Excellent. See you, Ben. Good luck. Okay. At that point, I'm going to go ahead in the interest of time, so you'll have time to watch it before the exam. Oh, yes, John. Yeah. Hopefully the video uploads in time. Thank you. I hope it uploads in time because it takes a little while. I have to close the Zoom session and then reopen it when I'm recording the video. But anyway, we're going to, oops, wrong page. What? Oh, good. That's good, John. I'm glad to know that. Yeah, I prefer online courses personally, more flexibility. So, our final module is ACLs. A bit longer, but we probably won't take too long here. So, as I was telling Ben earlier before the meeting, access control lists are sequential lists of statements that are configured to make routers filter packets. So, you could think of it kind of like a firewall. It's kind of like making your router have firewall capabilities. It's a little simpler than a firewall, but it does a pretty good job of what it does. It's another layer of security. This filtration is controlled with statements that either permit or deny certain packets based on certain criteria, depending on which type of ACO you use. You can filter on source or destination IP addresses or subnets. You can filter on certain network protocols such as ICMP, TCP, UDP, BGP, and etc. You can use source or destination TCP/UDP port packets, or ports, I mean. For example, you can block port 80 to prevent web traffic. And then you have TCP flags like SYN, ACK, RST, and etc. You can also block certain flags. ACLs are used to protect networks from unauthorized access and malicious attacks. ACLs have uses, but they also have limitations. ACLs, these are examples of tasks that ACLs can do. Should know this is not a be all and all list. This is not a comprehensive list. This is just examples of what it can do. It's not everything it can do, but these are just some use cases where you would want to use ACLs. ACLs can prevent any outside IP address from connecting to the telnet port of any of your networks. Telnet's insecure. You really don't want outside hosts to connect to telnet. You block it with ACLs. It's pretty easy. Just block the port. You can allow certain IP addresses to connect to the SSH port of a single server. You can also allow anyone to connect via HTTP or HTTPS to your web server. ACLs cannot do the following. They cannot specify which user can log in via telnet from the outside. In other words, it can block an IP address, but it cannot block a specific account. I should have probably specified that, but it does not know. ACLs have absolutely no way to know which user, like Poet2. If I was logging with telnet, it's there's an IP address, it's low, it's okay. But it's not going to know that I'm Poet2. It's not going to care. It doesn't know. It has no ability to know. So that's where ACLs kind of fail in that regard. They also cannot limit which files can be transferred out of your network. So, for example, if someone's taken some MP3s from your network or something like that, ACLs are not going to be a good way to keep that from happening. Finally, ACLs cannot prevent people from tunneling IM protocols, instant message protocols over outbound HTTPS connections. So yeah, I'm guessing that's like social media. I'm guessing is what it is. That's what the previous person wrote. But anyway, yeah, so ACLs can block this kind of stuff and allow this kind of things here based on addresses, network protocols, ports, and TCP flags. They don't really know how to do stuff from stuff or deal with stuff from the application layer. They don't know how to deal with user accounts, file types, like file extensions, and other protocols. They don't have any ability to control this stuff. Wildcard masks were already covered in the previous module or previous test, but Some of the OCPF wildcard masks are used in place of subnet masks when creating ACL statements. Why? Who knows? It's just the way Cisco made it. They control which address portions of incoming traffic are compared and ignored. Zeros represent the numbers that need to match, while every non-zero number is ignored. So a wildcard mask here in the subnet is this. This route will allow an address of 192.160.1.1. So note that, but not 192.160.2.1. So note these 3 zeros, they correspond to these 3 subnets. So 192.168.1, 0.0.0. So these 3 have to match for any incoming IP addresses. But notice how 2 in this third sub octet is not 1. It doesn't match the third octet. And according to our wildcard mask, the first 3 have to match this subnet. So therefore, this IP address is blocked. I am just as shocked as you are, John. I honestly expected him to go hard in subnetting because that's what our previous professor did. Again, I am just so sorry. He obviously has a different perspective making quizzes than I do. I really don't know how he does it. And he's probably not got a lot of time to do it. I'm so sorry. Hope that's why I'm reading from the PowerPoints this time. I have no idea how hard he's going to go on a specific topic or not. I just say study it all. And yeah. Yeah, it shouldn't be too many questions. You do have a paper too, I think, so which doesn't exactly tie to this. It can if you want to, but anyway, the next slides will the next slide will provide some examples on this process. So we're going to show you how to let me zoom in. This is how to calculate wildcard mass. Now you're not going to have this table in your exam, obviously, but we're going to use it here. You can use it here for in practice to compare, see how this works. So if you're given a question like find the wildcard mask for this subnet, so be sure to write this CIT mask in dotted decimal notation, convert the 255s to zeros, and convert the zeros to 255s. So 255 to 255 to 255 to 0 becomes 0.0.0, and then 0.0.0.255. Notice how the zeros and the 255s take a different place. If you look here, the wildcard, let me see if I explain that. Oh, that's a different question. I'm sorry. So find the wildcard mask for this subnet. So you write the CIT mask in the dot decimal notation. 255s come zeros. But the interesting octet though, look how we don't have a 255 or 0. So subtract the interesting octet from 255 to find the wildcard mask. So 252 is the interesting octet. Subtract it from 255 and you get 3. That's how you calculate wildcard masks that are not /24, /16, /8. Got one more here. 255 to 255 to 240 to 0. 255s come zeros in your wildcard mask. Subtract the interesting octet from 285. 255 minus 240 is 15. Then zeros become 255. Then we have ACL placement. So where you put your ACL rules on a router. So after creating your ACL statements, they are then assigned to a router's interface. Depending on their placement, ACLs process packets in 2 ways. So there's inbound and outbound. So inbound packets are filtered by ACL statements before routing statements are made. Outbound packets are filtered after routing decisions are made. ACL placement is determined by which ACL type you use. This is a crucial concept to understand for your labs, and you might also be tested on it. So let's see if I can explain it a little better. So if we got a router right here, say you're filtering what's coming out of or going out of the internet. So it's coming into the router. What you're working with is coming into the router. So it's inbound. It's made before the routing decision is made, so you put your ACL right here, basically. So that would be for an extended ACL, for example, it would be inbound. It's coming into the router before you send it out. So if we're making a standard ACL and it's coming into the internet, it's going to be here. It's going to be an outbound. That would be That would be an ACL after the routing decision is made. Does that make sense, or John? One more time. Okay, let me see what's down here. Yeah, we'll go over this one more time. Standard and extended ACLs will be explained in just a minute, but for this router here, let's say that we want to filter what our computers are sending out to the internet. That's going to require an extended ACL because we put extended ACLs as close to the source of the traffic as possible. This is inbound traffic. It's going into the router. So it's coming from our computers going into the router before it goes out or tries to go to the internet. We basically put the ACL on the interface close to the source as possible, and before it goes out to its intended or its expected destination, we want to filter this out before the routing decision is made. Now, let's say we have a host out on the internet, and it wants to communicate with one of our PCs. That would be outbound. So it's coming out from our internet, and it's going to our hosts, our internal hosts. So we would put that as close to the destination as possible. We would actually put that right here. So does that make sense? Good. That's very good. It'll make more sense when I explain. You're very welcome. It will make more sense when I get to standard and extended ACLs. So ACL types. There are multiple types of ACLs. There are standard and extended ACLs. These two are covered in this course. You will configure them, and you already have, or probably have, depending on your progress in the lab. There are also these three types. They're not covered in the course, and they shouldn't be covered. I put this note here. They're not covered in the assignments, quizzes, and final exam. I don't believe they will be. I can't guarantee it, but I'm hoping Dr. Sato will see that message there. These are just links. If you want to read more, I have some articles on it. But for the most part, just standard extended are all we need to know about. So there's also named ACLs. They're not an ACL type really, but you can name your access list. These names are beneficial as they can be used to identify the purpose of your ACLs and can help you insert, delete, and modify ACL entries and statements. Here's an example switch or router session using named ACLs. So IP access list extended Barney. So you can name your extended ACL list Barney, like you can name Barney Fife if it's going to be really, really strict. I don't know how many people are going to get that reference. But yeah, if you want a really, really strict extended ACL and we're going to have give it some personality, just call it Barney Fife. So yeah, you can name it and then you put your rules down. So yeah, you just start a named ACL by doing IP access list extended Barney or whatever you want to name. You can name it Fred. You can name it don't come in or whatever you want to name it. So let's get to the actual ACL types now. There are standard ACLs. This is a very basic type of ACL. It filters packets based on its source address, or filters packets based on their source IP address or subnet. They are identified with these access list numbers. So when you write out an access list number, you do like access list 1 or access list like 1300 or whatever, or 13,000. Standard ACL should always be placed as close to the destination as possible. This prevents packets from being unintentionally discarded. The following command template is used to create the standard ACL. You use standard or access list, then you use one of these numbers. Use permit, deny, or remark. Remark is basically like a comment. Like when you're programming, you leave comments. That would be a remark. So we can permit or deny a source IP address or subnet, and then you add the wildcard mask. You can also say host and then IP address or subnet as well, instead of putting the wildcard mask. The next slide demonstrates, if you're doing one host anyway, the next slide demonstrates how to create and assign a standard ACL. There are also more examples in the textbook. So I made this little diagram here. So we got Luigi here, and he wants to create we're going to create a standard ACL that prevents Luigi from sending packets to 172.16.1.0/24. Why are we blocking Luigi? I don't know. I guess the network admin wants to give him a hard time. So, conf t. So you start by writing conf t, access list 1 or whatever number you want. Your remark, stop traffic from Luigi. So remark is used to add a description to the access list. You can also do named ones like we discussed, but using remark lets you name your access list or give it a comment, I mean, to explain what it does. Access list 1, deny, and we are denying traffic from this subnet. So 172.6, or excuse me, this host. 172.16 or .16.3.10, then all zeros. When you're doing a host, it's just all zeros. Alternatively, you can block a single key or host with the host keyword. So you can just access list 1, deny host, and then Luigi's IP address. After that, you put IP permit. This allows everything else. You really need this. If you just deny, you probably aren't going to allow any other traffic in. You need to put implicit permit after your deny. You can also use the any keyword instead of doing this. So you can put IP address or access list 1 permit any. Then you pick the router interface you're going to put your access list on, and then you say in or out. So this is a standard ACL. We want it as close to the destination as possible. Luigi is going to try to connect to this subnet over here. This router is going to stop him. So it's a standard ACL. We don't put it on this interface because it's closer to the source. Excuse me. We need to put it as close to the destination as possible. This is the destination on the left. So we put it on the left interface. So Luigi's traffic's going to come. It's going to go into FA00. The router is going to make its routing decisions, and then it's going to reach this access list. Therefore, traffic is going to go out. So that's how you can do that. You can look at this. So if you're doing a standard ACL, it needs to go. You need to trace it from the source you're blocking from. It's going to go into the router. It needs to go in the interface. You need to put your ACL on the list or in the interface that the communication would go out of. So that'd be FA0/1 here. And you need to make sure you put out for standard ACLs. Does that make sense, John? Good. Excellent. So here's another type, extended ACLs. Extended ACLs are more robust than standard ones. They can filter packets based on source and destination IP address and subnets, source and destination TCP and UDP ports, and also protocol type and number. So TCP, UDP on ECMP, also like port 40 or port 80, port 22, port 23, so on. They are identified with a different number of access list numbers, like 100 to 199, then 2000 to 2699, or 2699. Extended ACL should always be placed as close to the source of packets as possible. Not necessarily required, but I mean, it does improve network performance. It's preferable to do. It's preferable to do it that way. Preferable, however you want to say it. The following command template is used to create extended ACL. This is complicated. It's a lot of stuff, but a lot of it's optional. So we're going to go through this here. So you type access list. You just type 100, 101, whatever. You can do permit, deny, or remark, just like the standard ones. Then you pick your protocol. You can pick TCP, UDP, IP, ICMP, or any. The source address and subnet, and then your wildcard mask of that source. Then you have the source port and the destination IP address, subnet, wildcard mask, is destination port. You can also put the keyword established. It's not really required. But anyway, we have extended ACLs. When specifying ports for extended ACLs, there will be instances where you need to list more than one port. The following list the keywords and it's used to specify ports. So LTN is less than. So all ports less than N. So less than ports 1023. So greater than, you can block or allow all ports above or greater than that port. You can just equal one port. You can not equal, you can just see all ports except for N. And then range, you can set a range of ports. So all ports N through M exclusively or inclusively. So range, you put port 1 to port 123. Include all ports, including 1 and 1023. Pages 48 to 51 in your Volume 2 textbook includes discussion on ports, including a table listing the most common port numbers used for protocols, such as Telnet, SSH, and HTTP. If you know your port numbers well, you should be fine. I don't know if you'll be tested on, but just in case, your textbook right here, this reference right here, I would say glance over that before you take your test. So a little more on ACL types. The established keyword is used to match established TCP connections. Matches packets with either ACK or RST set. Only first TCP packet does not have these flags. Used to allow response packets to outgoing connections. It's nothing you really deal with in this class, but it's just something to know. It just goes at the very end of like your first message or so. Not incredibly important to this class, but just something to know. ACL types, extended ACLs. So we got another example here. We got Waluigi trying to get to Mario, trying to probably send a mean message to Mario. We ain't gonna allow that, so we're going to create an extended ACL that prevents Waluigi from telnetting to Mario. So, or yeah, he's trying to connect to Mario's PC, try to put some mean messages or something on there. So we don't want that. So we're going to go on this router. We're going to conf t access list 101 remark stop Waluigi from telnetting Mario. So just a comment again to keep the same number, access list 101. We deny TCP host. We can use the host keyword just like in the standard one. We use Waluigi's IP address. Those how we work with hosts. You don't have to include the wildcard mask. It's a good shortcut. Then we have the source we're trying to block, and then we have the destination that Waluigi's trying to get to. And then we have 23, port equal 23. That's port 23 for telnet. You want to block telnet, you have to do equal 23. Access list 101, permit IP any. That is your implicit permit statement and allows everything else except Waluigi. So interface FA0/1. So that's the interface we're configuring. Notice that was the interface that's closest to the source we're trying to block. IP access group 101 in. When we're working with extended ACLs, you're going to use the in keyword. When you're using standard ACLs, you're going to use the out keyword. When you're configuring an extended ACL, you got your source. It's going to go to the router. You want to put your ACL right when it gets to the router. Before the router even has a chance to do any routing or routing decisions, you want to put that standard or extended ACL right there on this interface, FA0/1. So it stops Waluigi dead in his tracks. Man, he can't get into Smash, can't tell that Mario. Never ends for Waluigi. Okay, extended ACLs. Hey, I got to redesign the class. I can make it funny. Hey, who says tech can't be fun? Hope it's not too distracting, but I thought I'd make it funny. So extended ACLs, we got a little bit more of it. The last two here are a few more examples to show how to work with extended ACLs. Got some Sonic references here. I thought it'd be kind of funny. Got three routers here: Emerald Coast, Green Hill, Spagonia. Got different Sonic characters and different hosts and each of these networks. Man, this was fun. This was so fun to make. So we're going to use this network here. It looks a little complicated here. Just there's some ports here that might be a little hard to read, but I will speak everything out loud. So ACL types, we're going to figure some extended ACLs based on a scenario. The final I created actually had you do this with this network, and that's why I concluded these. I don't know if you end up doing that. It's probably not. But in case you are asked the question and not given a diagram, just be sure to know what to write. But I don't know if you have a question like that. I kind of doubt it. But anyway, we're going to do some ACLs based on some scenarios we need to work with. So we need to deny host shadow from sending HTTP traffic to Silver and Blaze. So basically all the hosts in the Spagonia subnet. Let's see. And then we are deny hosts. Let me see if we're actually covering that one on here. Okay. So this slide is going to cover this first scenario. The second slide is going to cover the second one. So we're going to deny shadow from all the way over here in Emerald Coast from getting to Silver and Blaze in Spagonia. So how we configure this? Extended ACLs need to be configured as close to the source or close to the source as possible. So we're going to configure the Emerald Coast router. We're going to go configure its F1/0 interface, which is connects directly to the shadow and to call hosts. So we're going to conf t on Emerald Coast router. Access list 101, deny TCP host. We're only blocking shadow. So we're going to do 10 1, that's 2 1, which is the IP address. We're going to do, so we're using the host keyword, so we don't need to include the wildcard mask. Then we're including the host, or excuse me, the destination subnet for Silver Blaze, because we're configuring more than one host, we need a subnet. So the Spagonia private subnet is 10.1.3.0/24. We're going to do 10.1.3.0 with the wildcard master /24, and then we're blocking HTTP traffic specifically, so we're going to put equal 80. Access list 101 permit IP any, that's our implicit permit. So if any of the other hosts want to send traffic to Silver and Blaze, we need to make sure that works, and that's what this permit statement's for. We configure interface F1/0 on Emerald Coast router connected shadow, IP access group 101 in. So when we're working with extended ACLs again, you use the in keyword because the traffic is going in to the router. If this was a standard ACL, we would be using keyword out. We'd be configuring the ACL on F1/0 on Spagonia as close to the destination as possible. So note how this access list was applied to the F1/0 interface. If we placed it on the other interfaces on Emerald Coast, our ACL would be ineffective. Plus, remember to always place your extended ACLs as close to the source as possible. So for example, if we put it on Green Hill Zone, the traffic may not even go that way. There's a chance it's probably not going to even go that way. We don't know how the routers are going to handle the traffic from Shadow to Silver Blaze. We have no idea. So that's why we put it as close to the source as possible. So we just stop it and there's no way it's going to get there. That's why we do that, especially in configurations like this where there's multiple routers connected to one another like this. Got the same network, new scenario. Deny all hosts on the Green Hill Zone LAN, Sonic and Amy, from sending any packets to any of the hosts on the Spagonia LAN. So, we don't want Sonic and Amy communicating with Silver and Blaze in any capacity. So, conf T on Green Hill Zone, notice again, we're going to stay as close to the source as possible. Conf T, access list 101, deny any. So we're denying anything from here, or any traffic at all. Excuse me, this is the traffic. We're denying any traffic from 10.1.1.0, which is the subnet, the private Green Hill Zone subnet. We're going to put the wildcard mask because we're working with a subnet, 0.0.0.255, 10.1.3.0. Again, we're protecting this destination, the whole subnet, 10.1.3.0, and then again the wildcard mask. We put our implicit permit statement, then again F1/0 on Green Hill, which is as close to the source as possible of the traffic we're trying to block. IP access group 101 in. Notice how this extended ACL did not use the keyword any for the ports. If you do not specify a port, simply leave that part out of your statement. That's a good point here. In your ACL, if you're blocking all traffic, you don't need to specify any ports. You can just use keyword any before your source and destination, and that'll cover everything. No ports need to be listed. Should ask or John, everything good? Does this all make sense? Excellent. So that should keep you that should help you all understand how to work with standard extend ACLs. Excuse me a minute. Editing access lists. So if you make a mistake on one of your access lists, you can just use the name of the ACL. If you name it, you can use its name and create a new statement or to add a new line. So access list 1, deny host 10.10.10.1. Added to the end of the ACL before implicit deny. You can actually just add that line to your ACL. Or ACL number, excuse me. So if it's not named. So let me start that over. To add a new line to your ACL, just use the same ACL number after creating it and applying it. And then you can just make a new rule. So access list 1. Any other modifications will need to be configured doing the following. So if you want to like delete a rule instead of just adding one or modify a rule, you need to create an access list with a new number, change the interface to use the new ACL, delete the old ACL, create a copy of the new ACL with the old number, and change interface to the old ACL number and delete the new ACL number. Basically you're deleting the old ACL, adding the old rules back, and making it. So if you don't name your ACL, you basically have to delete it all. You have to remember the rules, putting them into the new number. You can make it. You can delete the old ACL. Let me find. Okay. So you need to create a new access list with your rules, with the old rules as the new number. Delete the old ACL. Recreate the old ACL with its number if you want to. Put its rules in, and then you can delete the new ACL. That sounds kind of convoluted, but if you need to keep that number, this is what the steps you take. You basically it's like you can think of it this way. Say you got a box, a plastic box that's dirty. Its stuff is in it. You take the stuff out of it, put it in a clean box temporarily. Is saying or assuming that the stuff in that box belongs in there. You clean that box out, and then you put your stuff back into the old box and put the old new box back. Does that make sense? I think that's a better way of explaining it. A little convoluted, admittedly, but yeah. More details on editing access lists can also be found in your textbook. You probably won't need to do that if you're careful, but that's just there in case. ACL processing. ACL statements are processed sequentially. If rules matched, if your rule matches, permit or deny, the permit or deny action is taken. If not, the processing goes down to the next rule. So for example, if you have multiple rules, and say your traffic doesn't match that rule, say if it belongs to a different subnet, then it goes to the next rule. So the last entry just permits or denies any traffic. So if there's traffic we don't know of that we need to allow, we just put that implicit deny or implicit permit statement at the end, and it does that to anything else. We don't explicitly specify. For optimized performance with ACLs, place the most commonly used rules at the top. So instead of having common traffic go through all the rules it's not even going to use, just put your most commonly used rules at the top. Then it has to go through all the rules. Excuse me. So finally, applying ACLs to lines. On a router, use access class to assign an ACL to a VTY line. Basically, like it's one of those virtual connections for Telnet SSH. This allows you to control Telnet and SSH traffic to the router. For example, line conf t, line VTY04, log in, and you can set your password, and then you apply access class 10 in. And that concludes our study session. Any questions, John, before I end the recording? Okay. Hey, happy to help. I'm going to go ahead and let's see.